It's been so great to be back in person here at University of Michigan, my alma mater. And oh, wait, I should share my screen. And just seeing, it's been fabulous getting to talk to people and actually see, people in real life and get to talk about things that everyone is doing and seeing how campus has changed and what's the same and what's different here. So thanks so much for inviting me. I'm so honored to be here. So today I'm going to talk about the first, beyond the first portrait of a black hole. But before that, I just want to get into this idea of imaging the invisible. So what do I mean by that? Well, many things that we want to take pictures of are actually invisible to us. For instance, we can't take a picture of your brain using a standard camera. And in these cases, it's impossible to directly image the thing we want to see. And so we have to develop alternative ways to take indirect measurements, for instance, using an MRI scanner. And in these cases, the measurements don't look anything like the image that we're trying to capture. And so we have to design algorithms that work with the sensing system in order to recover the desired picture. And this isn't just true in medical imaging, but in a range of many different kinds of applications, a field referred to as computational photography or computational imaging. And as just an example, using this methodology, my group has been working on developing techniques to, for instance, estimate an object's material properties, improve medical images, and see under the ground for seismic, for studying earthquakes. But today I'm going to be talking about how we can use computational imaging to reveal what I think of as kind of the ultimate invisible, and that's black holes. So black holes are one of the most mysterious phenomena in our universe, and scientists have been studying them for years, ever since they were first predicted from Einstein's theory of general relativity over 100 years ago. And in particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation. So this galaxy, called M87, is 55 million light years away from us, and it's very special. And that's because over 100 years ago, someone discovered this streak of light on the sky, which ended up being a galactic scale jet of plasma that was shooting out of the center of the galaxy and marking the location of a supermassive black hole. And so over decades, scientists tried to develop better and better instruments to study the supermassive black hole at its center. And then in April of 2017, we hooked up this Earth-sized telescope and collected the data necessary to make a picture of a black hole. And 2 years after processing the data, this is what we saw. So this ring of light is a signature of a black hole's event horizon. But since it's so far away, it appears incredibly small in the sky. It's about the same size as a grain of sand. But if that grain of sand is in New York and I'm viewing it from where I live now in around Los Angeles, California. And so taking a picture of something that incredibly small required an international collaboration of scientists from all around the world, building new instruments and algorithms in order to make it possible. So I know many of you have already heard about a little bit about the story of taking the first image of a black hole. But today I want to tell you a very abridged story of how we were able to do that. And that will help in reminding you of the details that will help in motivating the majority of the talk today, where I'm going to be talking a bit about techniques currently being developed in my group at Caltech to push the imaging of black holes past its current limits and to see things that are still invisible to us. In particular, I'm going to be talking about new machine learning approaches my group is developing for doing uncertainty quantification of computational imaging pipelines, as well as how we are developing approaches to recover not just the static image of a black hole, but recovering the dynamics of a black hole over the course of a night as the gas is kind of swirling in. All right, so let's get started. So why is taking a picture of a black hole so difficult? Well, because this black hole, this shadow of the black hole is so small and can be only seen at a very particular wavelength, diffraction limits require that we actually build a telescope 13 million meters in size in order to see that ring structure. 13 million meters is essentially the size of the Earth. And although we couldn't build an Earth-sized telescope, instead what we did is the Event Horizon Telescope collaboration spent over a decade on joining telescopes located around the world to build a computational telescope the size of the Earth, capable of resolving the structure on the scale of a black hole's event horizon for the very first time. So how does this computational telescope work? Well, unlike within a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead we capture it in its frequency space. So we essentially take measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, if we tiled the globe in telescopes, we would collect all these measurements. But since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out that for every 2 telescopes we have in our telescope array, we obtain a single measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. But that means that if we have a small number of telescopes, then we only have a really small number of measurements. So for instance, in 2017, when we collected the data, we had 8 telescopes from around the world that were being used. But of those 8 telescopes, only 5 of them were at different locations and could actually see the black hole at M87. So that would be 5 choose 2, 10 measurements that we'd have to try to recover a picture of a black hole, which is a really small number of measurements. But luckily, as the Earth is rotating, we actually obtain other new measurements. So since the projected baselines between the telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane, where when telescopes are close together, we see low spatial frequencies, which tells us about broad structure. And so to get the detail we need to see that ring, we got to put the telescopes far apart. So how do we make an image after extracting these measurements? Well, at this point, we have this data, and we can kind of abstract away to all the astrophysics of it and think of it as purely a mathematical inverse problem. We have this sparse data, and our challenge is to invert those measurements to try to find the image that caused it. And if we were given measurements that covered the entire frequency plane, this would be trivial because in the case of no noise, you would just simply need to apply an inverse Fourier transform to recover back the image. But since we only see a few samples, that means that there's an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above each of the telescopes causes our data to be very noisy, and the problem becomes even more ill-posed. So to solve for the black hole, we had to develop a number of different techniques to kind of handle this challenging inverse problem. One of those techniques we refer to generally as regularized maximum likelihood estimation, which I'm sure many of you are familiar with as a general idea. But to briefly summarize the approach, we modeled the forward telescope system as a function f of x that returns the data we'd likely see, y hat, if the true image in the sky were x. Okay? And then, but that means that because we don't observe all possible measurements, since we have sparse data, that means that there's going to still be an infinite number of images, x here, that is going to give us exactly the same y hat. That's what's making the problem ill-posed. However, although there's an infinite number of solutions that are equally likely in terms of the measurement likelihood, of the images that are consistent with the data, some of the images we prefer over others. For instance, perhaps we think that the image on the left is too messy, and we prefer images that are sparse or compact, like the one on the right. Thus, our goal becomes not just to find an image that fits the data, but is likely under some sort of mathematical model of good or likely images. And so using this idea, we incorporate what we call an image prior or image regularization that essentially scores the quality of an image. And by solving for an image that maximizes both the data likelihood and the image prior, we can whittle down from the infinite possibilities to a single one that we think is a likely image that fits the data well, even in the presence of all that kinds of crazy noise that we've been talking about. Okay, so now in a super hand-wavy way, I've told you how you can go from this sparse, noisy measurements to a single image. How do we go about, writing that mathematically? Let's make it a little more concrete. So, and oftentimes, the way you might solve that looks like this. We solve an optimization problem where we're trying to find an image X here that maximizes the posterior probability conditioned on some observed measurements Y. And by simply rewriting this using Bayes' rule, we can see that maximizing this log posterior probability is equivalent to maximizing the sum over the data log likelihood and the log image prior. Those two terms that I just discussed in a super hand-wavy way, where the first one is that data fit, and the second one being the image likelihood, how much we prefer a particular image. But note that even if we can develop methods like these to recover a single image, we always have to be super cautious. And that's because any imaging method we come up with, whether it's a regularized maximum likelihood estimation problem or approach like this, or some fancy new machine learning approach, it's always going to require that we inject some additional information into the problem about what images look like to recover something back in the end. In the case of the regularized maximum likelihood problem, it's through the prior, which is highlighted in yellow. And in machine learning, it might be through something like the training set you use to train your model. And this injection of additional information is always going to bias our final picture. And for instance, we wouldn't want to be like, have this accidentally, even subconsciously, have this preference for ring images, and then be super excited that we recovered a ring back in the end. And so that meant a big question we faced in dealing with the M87 black hole data was not just how to make an image, but how do we verify what we're reconstructing with our imaging algorithms is real? And we tackled this by approaching the imaging problem in many different ways. One way we tackled it is by developing 3 different imaging pipelines. You can actually go online and download these pipelines along with the real actual M87 black hole data. So you can run the methods yourself or develop your own new methods. It's all there online. But we designed these pipelines here to have different hyperparameter knobs on them that control different modeling and optimization choices used when solving for the best image. So for instance, like what is the prior model that you're going to use or the regularization approach you're going to use? So typically the hyperparameters for these kind of methods are oftentimes tuned by a human user. But instead of having a human tune them, we wanted to instead search for the best set of hyperparameter settings to recover different types of source structures, and then see how those settings influence the M87 images that we recover. For instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no holes in the center, and we found the best set of parameters, beta here, to recover that disk shape. And then when transferring these exact parameters onto the M87 data, we found that although we had tried our hardest to find parameters that recovered a disk with no hole, our algorithm still required us to put a hole in the center when using the real data. And by doing this simple training and testing procedure on different kinds of underlying sources that we thought would trick us, we saw that our methods always preferred this ring shape. And that was true no matter the day that we observed the M87 black hole on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed everyone back in 2019, this ring of light surrounding the black hole. It's roughly 40 microarcseconds in size and brighter on the bottom than the top. And so this image really shows what the consensus of lots of different kinds of imaging methods found. There is no one image of the black hole, but this is showing you the consistent structure that we identified. Okay, so our goal here was to try to remove human bias from the final image as much as possible and use simple training data to select hyperparameter modeling choices. And this prevented us from tweaking the parameters too much by hand to just get something that we wanted in the end. And by doing that, we did get this ring shape, which is super exciting, but it doesn't answer the question of what is the uncertainty in this image? How likely is this ring? Did we just get lucky with the parameters that we selected in the end? So how did we go about doing that? So previously I talked about how we selected one set of parameters, beta, that perform best on our synthetic data. But why should there only be one set of parameters that we consider? In fact, by doing large parameter surveys, we found that there are many parameters that actually perform reasonably well on synthetic data sets. So instead of just selecting one set of betas, we instead set a threshold and found all the parameters that performed above that threshold on synthetic data, and then applied those to the real M87 data afterwards. So for example, for one of those pipelines that I talked about, we ran hundreds of thousands of different simulations and found about 1,500 parameters that we deemed acceptable by their performance on synthetic data. And once we had those 1,500 parameters, we could apply each of them to the M87 data to get 1,500 different images. And here is showing the results of that. So on the left is showing the mean image here on the left, and in the center is the standard deviation. And so you can see, okay, if you look at the standard deviation, there are areas that we do have more uncertainty in, that there's less constraints. You see these 3 knot regions on the bottom. And those knot, it turns out, is due to an interplay of like the point spread function of the telescopes with the source structure size. So you can see that those regions, okay, the flux, the intensity of the light in those regions is less constrained. But if you look at how bright what that standard deviation is relative to how bright that ring is in the mean image, you see it's only a small fraction of the brightness. So if you look at the fractional standard deviation, you can see actually we have a lot of faith in that ring structure. It appears in almost all the images that we reconstruct. But what changes a lot across the reconstructions is all that wispy structure on the outside. So you shouldn't believe all that wispy exterior structure. Okay, but what I really want to strongly highlight here is that what we're doing here is probing different modeling choices, like what is the prior that you're using, and then seeing how that is affecting our results. So in the regularized maximum likelihood estimation likelihood problem, we're essentially changing something like our prior term and then seeing how that prior affects our results. And that's definitely something that's important to explore because we have uncertainty in what that image regularization or image prior should be, especially when we're reconstructing an image of something like a black hole that we have never seen before, right? So it's important we explore that, but it's important to note that this is not a posterior distribution. It's not directly quantifying uncertainty due to the data under a fixed prior model. It's not characterizing the statistical uncertainty, it's more the systematic uncertainty. So for instance, why is this important? Well, oftentimes the energy landscape that you're optimizing is very bumpy, and finding a global maximum is a challenge. But even if you're super lucky to solve this optimization problem and find the global maximum, sorry, there's nothing to say that there isn't another solution that is almost as good that you shouldn't also consider. And so this ends up being a real significant challenge, especially for black hole imaging, where the problem is non-convex and the energy landscape can be super bumpy. So for example, here's a synthetic image of a black hole on the left, and we took this synthetic image and we generated synthetic telescope data from it as if the Event Horizon Telescope were actually seeing this image on the sky. So now we have this fake telescope data, and using this mock data set, we ran our typical regularized maximum likelihood methods on it to see what results we got. And we noticed that every time we ran the method with slightly different initialization, we would recover different results. In some cases, the image that we'd recover, the bright spot was in the top right, and in other cases, the bright spot was in the bottom left. And all that changed between them was just the different initialization. We'd start with a different random noise image, and it converged to a different location. And by evaluating the data likelihood of these, it appeared that both modes fit the data very well. So it was very hard to tell which one is the real one in the sky in this case. And this is not that rare of an occurrence because of the crazy noise that we experience on our measurements, we have to solve a non-convex optimization problem similar to a phase retrieval problem if you're familiar with that, and that sometimes has multiple solutions. So this can be a bit scary, right? Because it means that we had to manually explore the space of possibilities. And if this was real data and we didn't do this, we could be missing out on another image that would lead to a very different scientific interpretation. And so for problems like this, it's so important that we have ways to efficiently visualize the space of possibilities. Okay. Okay, so in other words, instead of computing something like a point estimate, like the regularized maximum likelihood optimization does, where you just find a single image that performs best, instead we want to sample from the full posterior distribution, the probability of X, the image, given Y, the data. And we want to do this in order to visualize that full solution space. Oftentimes, posterior estimation is achieved using sampling methods like Markov chain Monte Carlo, like MCMC. But these sampling and rejection approaches can be prohibitively slow and computationally expensive for high dimensional inverse problems, like when you're trying to solve for all the pixels in a full image. And so to tackle this, we recently have been developing new methods for efficient posterior exploration by exploiting deep learning machinery for the purpose of visualizing uncertainty. And in particular, what we're going to try to do is we're going to aim to learn a deep generative model to approximate the posterior samples of an imaging inverse problem. Okay, so we're going to take a little bit of a detour into deep generative models, and you'll see why in a minute. So I'm sure many of you are very familiar with the great success of deep generative models in machine learning and computer vision. What are these generative models? Well, given enough training images, we can train a neural network that takes as input random noise and outputs a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. Okay, so why am I telling you about this? Well, these deep neural networks define an implicit distribution over the space of images. And the impressive results that we've seen in the generative models work, it just indicates that these networks allow us to learn very flexible and expressive distributions that capture complex correlations in high dimensional images. So inspired by these generative models, my postdoc, Hassan, and I have been developing an approach to sample from a posterior distribution using a learned generative neural network. So our goal here is to learn the weights phi here of a neural network such that if you pass random noise Z to the network, out is going to pop a sample from the image reconstruction posterior. And different input noise is going to result in different posterior sample images. Essentially, all the neural network is doing is learning a mapping from a noise distribution to the target image's posterior distribution. Okay, so how should we go about training a network to give us this posterior samples? Well, unlike in the case of the bedroom generator or face generators or other generators that you see out there in the machine learning literature, we don't have a training set of images to use. If we did, if we had a training set of posterior samples, then we would be done, right? Because there would be no reason to learn a network to give us posterior samples if we already have those samples. All we have to work with, all we have is that sparse and noisy data Y of a single hidden image. So in our approach, which we call deep probabilistic imaging, or DPI for short, instead of using a collection of training images to solve for the neural network, as is typically done in other computer vision problems, instead we found that we could define a loss that is minimized when the weights of the neural network result in a distribution of network-generated images that best match the true image posterior. This is done by minimizing some kind of divergence between the two, and here I'm going to talk about it in terms of the KL divergence between these two distributions. But basically, all that's going to do is measure the distance between two distributions. So we want to find the network weights phi that minimize those differences between those distributions. And so this ends up being a very specific type of what is called a variational method. And so as a refresher, in variational methods, what we're doing is we define a simple family of density functions, for instance, Q phi here, which is visualized by this blue space of possible distributions. And then we solve an optimization problem to find the parameters phi that best match the target posterior distribution we're after, that little yellow star, where every point in that blue ball space is a full distribution over images. So we want to find the parameters that best match the actual true posterior distribution. But then the question becomes, okay, what should this family of variational distributions be that we're searching over? Traditionally, they were pretty simple, so that you could solve the necessary integrals and efficiently evaluate probabilities. So oftentimes, simple distribution families like Gaussian distributions are used. But in deep probabilistic imaging, by using a neural network, we can define a very flexible family of distributions parameterized by phi, which are the network weights here. And this flexible family of distributions can better capture the image posterior distributions that we're interested in targeting. Actually, DPI's optimization problem can also be intuitively derived by just extending the regularized maximum likelihood estimation method. So it turns out that the KL divergence between the distribution of images that the neural network produces and the true posterior can actually be rewritten as the expected log likelihood plus an entropy term, an entropy term on the bottom, on the end, where all that entropy term is doing is it encourages the distribution that the neural network produces to not collapse to a single solution. So you basically, if those two terms, at the first two terms are just like the ones that we saw in the regularized maximum likelihood estimation. So all we're doing is putting an entropy that says, make sure you don't collapse to a single image. So that means that in addition to understanding DPI as a variational inference method, it can also be regarded as a natural extension of doing uncertainty quantification for regularized maximum likelihood estimation problems. Okay, one last thing worth noting here is that in order to optimize this loss function, we need our generative model to be efficient in both generating samples and evaluating the likelihood of an arbitrary image. So that Q5 here, that's just saying what is the probability of an image X under my learned distribution Q5. Okay, so normal generative models though, such as GANs and VAEs, are only good at generating samples, but you can't easily evaluate a sample's likelihood to compute that entropy loss. So you can generate the sample from a distribution, but you can't say what is the probability of an arbitrary image under your distribution. So in order to accomplish both goals, in DPI we use an invertible generative model, a normalizing flow network, and this type of network can be executed in both directions. And as a result, we can easily generate samples of noise using the forward pass, and then easily compute the entropy loss using the inverse pass. Okay, so how does this end up working? Well, let's go back to that black hole example that I introduced earlier. So remember that for the ground truth image on the top, there ended up being multiple solutions that the regularized maximum likelihood would converge to when we reinitialize. So we sample a random image, and then we run our gradient descent from there, and we converge to those two solutions, bright spot on the top right and bright spot in the bottom left. Okay, so we had that solution there, but we ran our deep probabilistic imaging approach on this data to learn an approximate posterior distribution. So remember, we have one data set, then we train the network weights to produce a posterior distribution from that one data set. And then once we've done that, we can pass random noise through the network to sample from our posterior. So that's what's just being shown on the bottom, random samples of the posterior. And you can see here that the learned neural network also learns that there's, also indicates that there's two modes in the data. You have the bright spot in the top right and also the bright spot in the bottom left. A little harder to see here because but you can see it better if it's darker on my computer screen. Okay, so that's kind of exciting because it doesn't require any manual tuning or initialization like that. It just naturally falls out and is able to find this multimodal kind of distribution. But perhaps the most interesting thing is what happens when you run it on some real data. So this is a result that we got when we ran the approach on the real M87 black hole data. And what I find really encouraging is that if you compare the standard deviation of the resulting images to the standard deviation map we'd published earlier, you can see that they're amazingly similar. Although these standard deviation maps represent slightly different things, they're still comparable. And in both of them, they had these three regions of highest uncertainty that seemed to align. So this was really exciting to me when I saw this result, because it actually, the very first time Ha ran his method on the data, he got a result that was nearly the same as that we got when it took a whole group of scientists from around the world months to achieve through these grueling parameter surveys. And it only took about 1 hour of training time on a GPU. And so I'm really excited to be making progress on methods that allow us to better understand our uncertainty in these computational imaging systems more quickly. And it turns out that we found that this DPI framework is not just useful for black hole imaging, but it's useful for many different types of problems. Here are just a few applications we've been using it for in our group, from seismic tomography to exoplanet orbit fitting. And it's all just using the exact same ideas, just different types of data. Okay, but for now, let's get back to the black hole. So this image tells us so much about the immediate environment around a black hole, and it helps us get a better constraints on our understanding of gravity. But perhaps the most amazing thing that we learned from this is that by comparing the picture we've taken to simulations scientists have made for years, we find the image that we captured is amazingly consistent with the number of these predictions. But you might notice that the simulation I just showed you, it was actually moving. So you might wonder, is our actual recovered image of M87 also moving? And in fact, it turns out that it is. So another interesting thing is that we actually collected data of the M87 black hole over the course of an entire week. 2 days at the beginning of the week and 2 days at the end of the week. And we independently reconstructed each of these images, and we could string them together to a short movie, 4-frame movie. and one thing is, you notice if you play these, that you actually see some evolution, some variation in the bright distribution around the black hole. So here, I'll play it for you here. It's pretty tough to see, so I'm going to play it again, but you'll see the bright spot moves more from the left down towards the bottom. So studying evolution like this is quite exciting. It not only gives us a window into the dynamics around a black hole, and hopefully an understanding of how their powerful galactic scale jets are forming, but it also helps us in mapping the space-time of a black hole, which will help us in constraining the prediction of general relativity even further. But actually, the black hole in M87 is not the only black hole that we're interested in imaging to get a handle on the question of time variability. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's this cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the path of these clusters of stars over decades. And by tracking the motions of the stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is a supermassive black hole. In fact, this discovery led to the Nobel Prize in Physics given last year for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius Star. And so as awesome as the black hole in M87 has been, Sagittarius Star, or what we like to say Sag Star for short, might be able to help us better answer some of these questions. M87 is massive. It's 6.5 billion solar masses, billion solar masses. And as a comparison, Sagittarius Star is a measly 4 million solar masses. And that means because it's a lot smaller, gas orbits around it a lot more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around the black hole in M87, for Sagittarius Star, it makes a complete orbit every 4 to 30 minutes. So we'd love to be able to image the time variations around Sagittarius Star, but doing so is difficult. Why is that? Well, remember that the data that we used to recover the black hole image is actually collected over the entire night. As the Earth is rotating, we collect different measurements that together we use to make the M87 image. So we threw all those measurements into one pot and we tried to say what single image fit all those measurements. But since Sagittarius Star is actually evolving over the time span of just minutes, that means that every measurement we make is from a different snapshot of the black hole. So how should we go about capturing the black hole's evolution? Well, if we were just to apply the same static imaging methods as before and just try to reconstruct every little snapshot of data over the course of a night, the data is just far too sparse to use this approach, and it just results in uninformative gibberish. There's just not enough data to do that kind of problem. So clearly this naive approach isn't going to work. So how should we capture and learn about the black hole's evolution then? Well, we've been working on ways to extract black hole motion that we observe from this data. And the first approach that we took was to develop methods to reconstruct full movies of the black hole evolving over the course of a night. But if you thought recovering a static image is a hard, ill-posed problem, this is orders of magnitude more challenging, because now we have the exact same amount of data, but we're trying to solve for all the pixels in a full video rather than just a static frame. And so to get around this, you often have to include a significant amount of temporal regularization into the optimization problem in order to get a good result. What this means is that we just have to say that neighboring frames are something like they're very similar. And so you have to crank that regularization up so much that oftentimes the reconstruction you're able to achieve is missing a lot of the rich dynamics that you're really after. So here on the left is showing a synthetic ground truth video. And on the right is a video reconstruction obtained from using this method where we kind of assume like the measurements look a lot like the ones that we get from the Event Horizon Telescope. And so here you see, if you look at the video on the right, okay, we've recovered something like the average structure of a black hole, and there's some evolution there too that we see over time. But it, you know, and that is a lot better than the random gibberish that we saw before. But you know, we're missing a lot of those rich dynamics that we're after. We don't see all that wispy structure, and the information about how those wisps are moving around can be really helpful and informative. So although imaging is crucial in making sure we give ourselves the flexibility to see something totally surprising, perhaps if our ultimate goal is to understand the underlying motion field, this is not the final result, the final method that we should be using to get to that. Alternatively, you could also imagine wanting to describe the underlying flow using something like a physical model of black holes. For instance, we could search in the space of parameters that produce different synthetic black hole videos and try to find the parameter settings that best match the data that we've observed. And while this theoretically may be possible to do, in reality, currently this is just too computationally expensive. Simulating just 60,000 static image snapshots of a black hole that we did for the M87 papers took over 75 million core hours to complete. So doing something like this, searching over the space, would be very computationally challenging in a naive way, at least. So there's this spectrum of different approaches that one can take in trying to recover the underlying motion of a black hole. On one end of the spectrum is recovering a non-parametric flow field, which is a maximally flexible, but requires us to recover a movie of the flow field. And in the end, it might not even be that interpretable. And on the other end of the spectrum is estimating the parameters of a physics-based black hole model. And while this result would be maximally interpretable, this approach has the disadvantage that we're tied to a particular black hole model that honestly is probably not correct, and therefore is overly restrictive, and also is computationally expensive. So rather than picking one of these extreme options, we'd like to try to find some middle ground. Use a model that balances the pros and cons of these different approaches while being computationally efficient. And towards that end, we've been working on modeling the persistent evolution of black hole sources as the result of a stochastic advection diffusion process and solving for the underlying parameters of this model that best fit the observed measurements. So this intermediate option that I'll introduce tries to find an interpretable compression of the motion field by asking us only to match the persistent motion statistics. This work is being led by Aviad Levis, who is a postdoc in my group, but also with our black hole physics collaborators, David Lee and Charles Gammy, who are at UIUC, as well as Joel Trop, who's an applied math at Caltech. Okay, so let's dive in to understand a bit better. So here I'm showing the equation of a stochastic partial differential equation, a PDE, that is describing an advection diffusion process. Don't worry about understanding the equation, don't have to understand it. I'm gonna just point out the relevant details here. So in this process, there are two parameters that we really care about, V and D, where V is the velocity field that describes how the bulk is moving, and D is the diffusion field, which describes how material spreads out in space. So for instance, these two cups contain water with different non-isotropic diffusion fields, resulting in the dye spreading out differently in them. And therefore, you can imagine describing the motion field of the dye using a PDE like this one with different underlying parameters D. So in this work, we use a black hole motivated fluid model to parameterize each of the fields with one parameter each, theta1 and theta2. And by solving this equation for rho, we can obtain a movie that obeys this advection diffusion process under different parameter settings theta. So for instance, for this particular choice of theta1 and theta2, we put input noise into the system, and out is going to pop a video here that has this like fluid flowy spiral motion to it. And by tuning these parameters appropriately, you can see that we can produce flow fields from this model that when paired with a physically motivated envelope can mimic that of the smoothly evolving black hole simulations like I've been showing throughout the video. Oftentimes these can trick us actually, even though they're not at all black hole simulations. Okay, so great. So our goal here is then to find the parameters theta that best describe our observed source motion. But there's a catch, and that's that this is a stochastic partial differential equation. That means the fluid flow movie we get is very dependent on the input forcing term epsilon. And therefore, two random fields with the same underlying velocity and diffusion parameters are going to result in very different pixel values over time. The general swirling structure is going to look the same to the eye, but the actual individual pixels are different over time. And therefore, a key challenge to estimating the dynamics is that the pixel values are driven by this unknown random source, which we do not want to estimate. We don't want to have to estimate a movie of noise, basically. And so an insight of our work is that by using dimensionality reduction, we can ignore that epsilon term altogether when determining the parameters that best fit the dynamics of a random field. So, okay, roughly how does this work? Okay, for a given parameter set, theta 1 and theta 2, what we can do is extract the top modes, which capture most of the variability of the stochastic partial differential equation under those parameter settings. We don't actually have access to a matrix operator, so we can't do something like, like a SVD decomposition or anything like that. And that's a challenge because the matrix is so large, we have to use matrix scheme methods. So I'm not going to talk about it here, but if anyone has questions, I'm happy to talk about it later. Okay, so let's just say we have those parameters, we get the top modes from the stochastic PDE, and then what we do is we can compute the projection of the random field we see in the sky, that swirling structure around the black hole, we can project it onto the top modes. And if that subspace represents the random field in the sky well, then that projection residual will be small. And parameters that are different from those that generated the random field will result in a subspace that does not capture the random field well. And therefore, the projection residual will be high in that case. But by comparing the projection residual for different parameters, we estimate the underlying true parameters as the global minimum to this projection residual loss function. So once we've done that, once we've collected the projection residual for each of the different parameters that we're interested in, then we can say, okay, which one is the global minimum in this case? And then we can take those optimal motion parameters that theta 1 and theta 2 that represent the velocity and diffusion fields, and then we can draw a new fluid flow models with the same parameters. So it's not going to individually match the true black hole motion in the sky, but it's going to have the same statistics of the motion in the sky. And by merging this flow realization with an envelope that we optimize jointly with the dynamic parameters, we can generate a movie that we believe is sampled from a similar stationary distribution as the true underlying video of the black hole. Obviously, these are different. The fluid flow model is not a real model of black hole dynamics, whereas the one on the left that we're trying to estimate from actually is a model of what we think black holes, how they're evolving. But notice how the video on the right is still able to recover something about the fluid flow and the behavior of things like the wispy structures, even though these models do not match exactly. And so the big advantage of this approach is that we can get parameters that are interpretable, but we still have the flexibility to see something a little bit surprising. And we have seen that these velocity and diffusion parameters that describe these different gas flows allow us to connect to other scientific parameters like the spin of the black hole. So we can try to recover other scientific information from these, even though it is not explicitly a model of black holes. Okay, but if you paid close attention, you notice that I assumed that I actually had the true video in the sky, the true video of the black hole, in order to calculate that projection residual that was used in our loss. But we don't actually have the real black hole video in the sky, right? Instead, we only have these sparse and noisy measurements. So what are we supposed to do in this case? Well, actually, it turns out mathematically, at least, to be a quite simple extension to optimizing the measurement spaces alternatively. And when we only have measurements to constrain the flow parameters, we can still recover the dynamics decently, even with the sparse measurements that mimic those that were captured with a very sparse event horizon telescope array. So here we can see things like we get the general rotation of the motion and stuff, even though we're only working with that sparse data. And that looks good. We get some information that's useful, but it looks a lot worse than what we were seeing before when we're fitting directly to the video. And so as important as it is to continue pushing on the algorithmic approaches to try to squeeze more out of the data, it's important to also realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And to that end, we've been working on improving the actual Event Horizon Telescope network. In 2017, we observed with telescopes at 6 different locations around the world. And since then, we've been building up our array to add more data, adding telescopes in Greenland, France, Arizona, and then the one I'm most excited about is we are starting to add a telescope at Caltech's Owens Valley Observatory. So my new home is also becoming part of the Event Horizon Telescope. But this is really just the beginning. Our goal is to add 10 more telescopes around the world that fill up that measurement space so we can get much better data and much better results. And by using a proposed future array, we've started to see that we can improve our dynamic recovery results from something like this to something like this, recovering a fluid flow model that's incredibly similar to the best fitting flow model when we actually use the black hole movie directly. So we get much more information about not just the direction of rotation, but actually things like the angle that those wispy structures are coming off the black hole. And so using this approach, we may be able to not just recover the general structure of a black hole in the center of our galaxy, but actually capture the properties of the gas as it's circling towards the event horizon. But we're not done there. In fact, we've recently been trying to take this one step forward and actually recovering the dynamic structure around the black hole, not in its projected 2D, but actually in 3D. So I want to take 2 more minutes to describe that, and then I'll finish up the talk. Okay, so light propagating in that black hole doesn't actually follow straight lines. It's curved because the black hole is actually curving space-time. And so photons can even go in complete circles around it. So we have lots of photons that are flying around everywhere from the hot gas, and some of them are too close and they fall into the black hole, but other ones just graze it or are bent by the gravitational pull, such that the net effect is the black hole casts a shadow on this backdrop of hot material that's almost perfectly circular. And this bending of light is referred to as gravitational lensing and causes all these ring-like images that I've been showing throughout this presentation. But if you plug in all the physics, then actually this ring doesn't look like this. It has non-uniformities in the spinning gas, and you might notice you'll get something more like this. And you might notice, it's a little hard to see here, but every once in a while you might get a brighter flare, something called a hotspot. And tracking these hotspots is super important scientifically because watching how those hotspots evolve and shear out gives us a window into the space-time around the black hole. So being able to actually map these 3-dimensional hotspots around a black hole would be super exciting and lead to some big scientific gains. But how do we go about actually seeing these hotspots in 3 dimensions? Well, we only have these gravitationally lensed 2D projections. And even more than that, we only have them coming from one direction in the sky. We're not seeing it at different orientations. And in fact, as you all know, we have less than that. We only have the measurements. So we have measurements of the projections from one orientation in the sky. But by building in our expected knowledge about physics around a black hole with modern ideas in deep learning using neural radiance fields, we've been able to demonstrate that it may be possible in the future to actually do a 3D reconstruction of the environment around a black hole over time. Of course, in this case, we have to start plugging in more and more physics to try to squeeze more out of the data. But looking at this balance between your complete flexibility and adding more physics to get more information out, it's really exciting to be able to see what you can do if you allow to blend machine learning and physics together. So this is hot off the press, something I'm super excited about. Hopefully in the future, I'll get to tell you more about it. Okay, so to close, it's clear we've learned a lot from the image of the black hole in M87 already. But what I hope I got across in this talk today is that we're really just at the beginning and there's still so much to come. And hopefully one day we'll be able to show you not just a static image of a black hole, but actually a movie of a black hole as the gas is slowly falling towards the event horizon, and perhaps maybe even one day in 3 dimensions. And so with that, I want to thank the amazing team of Event Horizon Telescope collaborators that I work with on a daily basis, a team that's very much still hard at work. In fact, holding our very first in-person meeting for the US contingent in a number of years, just a couple weeks ago. But in particular, I want to highlight Hassan and Aviad Levis, who have been amazing and have led the work that I've mostly discussed today. So thank you, and I'm happy to take any questions.
Great, so if people have questions, feel free to raise your hand and someone can run a mic up to you. I'll also be looking on Zoom in case there are questions from people online.
I just want to ask, how were you able to determine the color of outside of the ring? Because you said it was not a telescope, it was just the wavelengths, right?
Yeah.
So how were you able to determine the RGB values or HSL values? Because it's not the light which is coming, it's just the wave.
Yeah, very good question. So that's fake. It's a pseudo color. So we basically just have a grayscale image, And the color on top of it is a perceptual color map, perceptually uniform color map that we use just to help you distinguish the areas a little bit better. And we had, honestly, like we spent a lot of time even on things like what color map should we use? We wanted it to be perceptually uniform, but otherwise should we use red, blues, purples, like what color to use? And in the end, we decided on this more reddish orange because it gives a feeling of heat. And the gas around the black hole is hundreds of billions of degrees. So that's the reason. It's all one wave. It's a 1 millimeter wavelength, so it's not in there is no color associated with it.
I was curious what kind of noise model you're optimizing for in the log likelihood. And do you ever consider heteroscedastic noise, where the noise can have different variances across nights when you're imaging with
What kind of noise?
heteroscedastic noise? So when the noise variance is different, so when you're imaging across different nights and the atmospheric conditions are different, do you ever encounter something like that?
Yeah, great question. So let me just go back to that equation I showed here. Yeah, so what we do is we have, from first principles, you can derive what the Gaussian noise would be for a measurement from a pair of telescopes by looking at things like the aperture and the bandwidth and integration time that we use. But that's not that challenging of a noise. So what we're very, so I didn't have a chance to go into this, but basically, the measurements that we get are interferometric measurements. So we have like the data from the black hole, light comes off of it, right? And it travels to Earth for 55 million years. And then when it reaches Earth, it reaches one of the telescopes slightly before the other one. And that slight time delay is the key for extracting the 2D spatial frequency measurement that we use for image reconstruction. But actually, above every telescope around the globe, there's a different atmosphere. So there's a different atmosphere above Chile than there is above Spain, then there's above Hawaii, and that additional atmosphere adds an additional propagation delay. So if we care about that time delay, now that's completely scrambled. And what that ends up doing is it adds a completely random phase. So we have our 2D dimensional 2D spatial frequency measurement, which is, you can describe it with an amplitude and a phase. The phase is totally scrambled by the atmosphere, and this happens on it's 1 second time intervals. So we basically can't use the phase directly. The amplitude is also corrupted because the amplitude, it varies over time as well, but that is a lot more stable. So we can try to correct for the amplitude somewhat. But basically, because the phase is totally scrambled, we can't use the absolute phase directly. And what we do is we use these things called closure quantities. And so what this says is that if you have telescopes in a closed loop, even though between every two telescopes that phase is scrambled, if you close the loop, because every measurement is with pairs of telescopes, that additional air due to the atmosphere actually cancels out completely. And you're left with a term that is the same as if you didn't have any atmosphere. And so what we do is we kind of fudge this a little bit. It's not, we write it in terms of the closure quantity. So we define these new data products. And those are higher order data products, so they're not actually directly the Fourier components themselves. It's multiplications of Fourier components, and so on top of those, we have a Gaussian approximation. So if you believe your signal to noise ratio is high enough, then you can approximate that as a Gaussian. And so that allows us to remove the atmosphere from the problem. It comes at the cost of it no longer being a linear inverse problem. And so that makes it a lot more challenging, which causes that non-convexity and stuff. But of course, you would have that be the case even if you did solve it in a linear way, because the noise would be, basically you have no information on the phase in that case. So I hope that kind of answered your question. I'm happy to try to go into more detail with you one-on-one if you want.
We had a question online from Dichong Zhang. Is there any reason why you prefer normalizing flows or other sorts of generative models with tractable likelihood like pixel CNNs?
We haven't, so again, comparing to things like GANs and VEs, it's really about that computing of the entropy, but there are other ways as long as they're invertible. As long as you can have some way of going back and actually computing the likelihood efficiently. We haven't explored a lot in that. We did do things like it does matter a little bit what your architecture is, especially with the normalizing flows, because they're a lot less expressive than other types of architecture. So things like glow models versus here we used a real MVP, but glow models were a lot more challenging to kind of get multimodal kind of structures that kind of came out of them. So I think I haven't looked into other ones and haven't tried other ones, but it's definitely an area that we're interested in. Yeah.
I just asked, it's a very interesting talk. So I have a very general question. I think a lot of your hyperparameter tuning is based on the physical simulation, and you're trying to mimic the results of the physical simulation. So is it possible that your hyperparameters is biased towards the physical models? And in fact, the physical models, there are still many hyperparameters in their simulation itself. And what's happening in the supercomputers that is simulating the high resolution results is pretty different from what is happening far away in the M87 galaxy. So the result you're reproducing is somehow also biased.
Yeah, it's a great question. But basically we wanted to avoid that using physical models altogether. So although I showed a bunch of physical models in this of simulations in this talk, actually when we were doing imaging, we explicitly did not use any kinds of what we call GRMHD simulations that are basically modeling the black hole. Those were not at all used in selecting hyperparameters. We used very simple geometric models like disks and rings and double structures and things like this that had similar data properties of things that we saw in the data, a bounce structure and basically low-level data properties that we saw, that we used very simple models that were not at all physically motivated. and that's what we use to tune them to kind of get very different types of images. So as just an example here, we have like some, like you see ring, crescent, disk, double source, these kind of things. There's not, there were no models of black holes that were used at that stage. Now, once you get an image of a once you get an image and you see it has this ring-like structure, then you can ask yourself, conditioned on it being from this model, can I tease more out of the data? And so there were a number of papers on that, of looking at it from a modeling point of view, where you assume it's a crescent, or actually fitting the, making a library of simulations and seeing which parameter spaces best fit the data. But that was all done after imaging was done, and we were confident in that ring shape. Hope that answered your question. Good question.
Thank you.
Hi, yeah, you might have answered this, but are there laminar and turbulent flow regimes, and are you able to kind of predict them based off of boundary conditions that your model might give you, or is it not so similar to like traditional fluid dynamics?
Yeah, not the right person to answer this question. They're definitely turbulent fluid flow and stuff, and the parameter spaces, you should look in the papers to see how they were able to narrow the space down. Actually, a lot of the way to narrow the space was not just using the image itself, but actually using it with multi-wavelength data and using the combination of that to try to tease down what the parameter spaces are. But I think all of the, I'm not, they model these different sane and mad simulations with different, properties and stuff. And you should look in the papers for more detail. I don't want to say anything wrong here.
We had a couple more questions on Zoom. One from Al Hero. It's not clear how you accounted for or compensated for atmospheric disturbances, and could the quality of your images be improved if you back out the atmospheric distortions, as might be done in active optics?
Yeah, so again, in this, good question, in this, I didn't go through it, but in this equation, okay, maybe I'll just go back to the simpler one here. In the likelihood term, we write this in terms of a data product that is invariant to the atmosphere. We'd write it in terms of these closure quantities, closure phase, log closure amplitude, and these cancel out the effect of the atmosphere at the cost that you're solving now a nonlinear inverse problem. So it's no longer a pure likelihood, because there is some the same data appears in multiple terms, but it's a good way of trying to avoid the effect of the atmosphere. Now you could go about it by saying, okay, I want to solve for all the gains, complex gains at every telescope site, and I solve for that as a different, like as a parameter that I solve for simultaneously. You don't have a strong prior on that, but you could do that instead of using these closure quantities. And some of the we didn't do it in this work, but in some of the model-based code where you're doing like crescent fitting directly, they do that instead of solving for closure under closure quantities, where the atmosphere cancels itself out. You instead solve for the gains directly. And the only reason you're able to do that is because there are n choose 2 measurements, but there are n corrections. So there are more measurements than you have corrections, and it allows you to solve for that as well. But it's a little bit of a trade-off in how you go solving for it. I think in the future, we'd like to add that into the posterior as well. So solve for it directly, and then you have a real likelihood instead of this kind of fake likelihood that we're using right now. But if your signal to noise is greater than 1, it's a pretty good approximation to use the closure quantities. It's pretty close to the posterior that you get if you use the directly. I hope that answered the question. Was there a second part to the question, or?
Could you improve the quality of the image by backing out the atmospheric distortions as in active optics?
Oh, okay. So yeah. So I think you could improve a little bit, but again, I think that is in the future as we start to add more telescopes to the array that are smaller dishes, your signal to noise is not going to be as high. And so using something like actually modeling the calibration terms directly and solving those simultaneously might help you in the end. So it might be good to, for instance, get a first initialization using something like closure quantities, and then go back and solving directly where you have the true posteriors that you're using, not this approximation. And then as far as adaptive optics, which is a method often used in optical astronomy, where you have this guide star and you see how it's distorted, the atmosphere distorts it, and then you figure out how to undistort your images based upon how the atmosphere is being distorted. Unfortunately, in radio, we don't have the ability that, like, what they do is I think that they bounce the light off the atmosphere. And in radio, it's just going to go straight through. So we don't have the ability to have it bounce off and get that guide star in the same way. You could imagine having some sort of beacon or something. You have to be above the atmosphere. We've talked about this idea of like having these high altitude drones. Then you have to like have them really stable and moving really fast. So it would be, not impossible, but it would be a huge technical challenge to get something like that working. And I think as an alternative, we've been thinking more about putting more telescopes on the ground, and that's actually probably more, then you have more constraints, and so it's actually an easier problem to solve in that case.
This is incredible. That's why I just have another question. So, so like there's one like you mentioned in M87, and there's another one which is like closer. Do you think the one which is closer, it's like that one is like the better in terms of observation, or the one which is far away? Because like black holes are like the the darkest black thing, and
Yeah.
The light waves like deviate from them. So like if they're in the distance, from the distance we can just see like where the light waves goes. But like if it is closer, we cannot like see where the light waves goes, right? So like but at the same time, if it is at distance, we cannot see like the light waves coming through. So like I'm just like asking, like, is the one which is like closer is the better for observation, or like one which is at the distance?
Yeah, good question. So it kind of depends on, so definitely the one that's closer, Sagittarius Star, is the holy grail. That is the one we really want to be able to measure, because that one is closer to us and we have better constraints on it. So for instance, prior to us collecting any data, there's work from other teams, for instance, like the one I talked about in Germany and at UCLA, that they have measured, for instance, the weight of the black hole probably to a better precision than I know my own weight. So they have like a really good estimate of the mass of the black hole. And so what that tells us is actually, okay, so there are two parameters that really determine that shadow, that feature of light, that ring of light around the black hole. It's the mass and the spin. So if you know the mass, then the only other thing that you care about is the spin that describes what that shadow looks like. And the mass really has most of the effect. So the spin changes, it's like a plus or minus 4% change on the shape and size of that ring. So the mass is like so if we already have a mass constraint and we see a ring that aligns or doesn't align with that, that's really informative. And we can do, that helps us a lot in constraining our prediction of, the GR and stuff. Whereas for MA7, actually before we made the image, there was a huge discrepancy in what that mass could be. Different kind of approaches, ones that use gas dynamics to model the mass, estimated about 3 billion solar masses, whereas stellar orbits predicted around 6.5 to 7 billion solar masses. So there was like this factor of 2. And so when we saw the image, and really the stellar orbits was like an upper bound to what you could have. And when we saw, it aligned very closely with the stellar orbits, but there was already this huge error bar on that. Whereas for Sagittarius Star, as I said, there's really tight error bars. And so that helps a lot in constraining a GR. Okay, so that's great. We'd love Sagittarius Star, but Sagittarius Star is our problem child. And that's because it evolves really quickly, as I've talked about, which is much harder for making an image. Also, there's this interstellar scattering between us and the black hole, which is basically like making it like we are watching the black hole through a frosted window. And so these two effects, I would say the time variability is a lot more of a problem, but those two effects together make imaging the black hole a lot harder. So that's why in the end, we made a picture of MA7 fairly easily. Sagittarius Star, we've been working on it, but it's much more challenging to get around.
So I was really interested to see how you're applying these methods to different fields such as seismology, medical imaging, and exoplanets.
Yeah.
So I was curious if there's any other kinds of imaging you're hoping to do with these methods, or anything you and your team are excited about, and also kind of what exactly you're learning about exoplanets with this imaging.
Yeah, so I guess like one thing I'm just really excited about is I love connecting to these different interdisciplinary fields because I don't know, it's just fun and it's a way to learn about a new topic, and I don't know, I enjoy it, faking my way through it. But what are some other areas? Oh gosh, okay, yeah, I've done a little, so again, one of my students is working in medical, one in seismology, one in, we've also been starting a little bit on climate science kind of stuff. We've done some stuff with looking at images of embryos for purposes of trying to improve IVF and stuff. We've done I've done a little bit of robotic stuff. So I don't know, but they're all kind of, they sound very different, but at their core, they're all exactly the same problem. You have messy data, try to use some sort of structure to recover something, to try to find some hidden information from it. And a lot of times what I like to do is try to build in, domain knowledge in doing that. That is part of the structure. So you could use structure and like, what is the structure of images, or what is, that's all, and you can learn that structure purely from machine learning, or you can try to learn it from machine learning and inject some knowledge about what that structure should be. And so I like to solve these like inverse problems with physics based or some sort of underlying model. And then for exoplanet orbit fitting, so who worked on the deep probabilistic imaging work during his PhD, he worked for the Roman Space Telescope, which has a goal of imaging exoplanets. And so they use some, maybe I have the picture here. What they have is they actually have direct images of an exoplanet over time. And you can see here's like an exoplanet going, traveling around a star. And basically you only have this projection of the exoplanet. And what you want to do is try to learn the orbit. What is the parameters of the orbit in 3 dimensions from that projected data? And so what we've been doing is from those measurements, recover the posterior distribution of orbits. And that can help you in getting things about like, okay, what is the, does this seem Earth-like, or, is more and So that's the kind of ultimate goal, to understand things like that. But he's been teaching me about the exoplanet orbit fitting. So again, kind of fun learning about new topics through the people I collaborate with.
We're at about 12 minutes past the hour, so I think we're going to wrap it up here. So thanks again for the awesome presentation and very engaging Q&A session.
Thanks for